the concept of union and intersection are also useful in geometry. For example, sometimes we may be interested in finding the intersection of two curves. Okay, take one example. You take the unit circle. Unit circle can be represented as I told you, the set of all ordered pairs xy such that x square plus y square is equal to 1. This is a unit circle. Circle is actually a set of points, and all the points on the unit circle satisfy, all the points can be represented as an ordered pair xy and of real numbers, and the points are precisely the points satisfying x square plus y square is equal to 1. Suppose you take a line like this, the set of all xy in R2 such that 2x plus 3y is equal to set of all ordered pairs xy such that 2x plus 3y is equal to 2. Or we say that this 2x plus 3y is equal to 2 is the equation of this line. Now we are interested in the finding the intersection of these two curves. Sometimes, and the intersection, suppose this is A, this is the set B, you can take the intersection. The conic sections can be thought of as the intersection of a cone and a plane. So intersection comes very frequently in geometry. Suppose A is the set of all divisors of 10. Suppose A is the set of all divisors of the set of all positive divisors of 10, and suppose B is the set of all divisors of say 12. Then A intersection B will be set of all divisors of set of all positive integers which divides both 10 and 12. What will be that? That will be just 1 and 2. If you take the set of all multiples of 3 and as A and the set of all multiples of 2 as B, the A intersection will be the set of all integers which are multiples of both 2 and 3, that is multiples of 6. Suppose A is the set of all 2n minus 1 where n is an integer, and suppose that B is the set of all 2n plus 1 where n is an integer. All integers, all numbers which can be written as 2n minus 1 for some integer, that is A, and all numbers which can be written as 2n plus 1 for any integer, that is B. Then it is easy to see that A and B are equal. How to prove that A and B are equal? You prove that A is a subset of B and B is a subset of A. That is, you take an element. How to prove that A is a subset of B? We take an element of A, and that will be of the form 2n minus 1 for 2n minus. So that will be of the form say 2n naught minus 1. Now I can write the same thing as this is just 2n naught minus 1 What will be this? This will be 2n naught minus 2. Clear? So 2n naught minus 1 will be, plus 1 will be 2n naught minus 2 plus 1, that is equal to, what I meant to prove, I want to prove that that is this can be this is an element of 2n plus 1. So how to do that? 2n naught minus 1, I want to write it as in the form, how is that possible? This is nothing but 2n naught minus 2 can be written as 2n naught minus 1. So, it's the other way. 2n naught minus 1. You can write it as 2n naught plus 1. 2n naught plus 1, what will be that? 2n naught plus 2. And 2n naught plus 2 can be written as 2n naught plus 2. So so we start with an element 2n naught minus 1 and write it as in the form 2n naught plus 1. How is that possible? Yes, you put you take n naught minus 1. If n naught is an integer, n naught minus 1 is an integer. So 2n naught minus 1 plus 1. What will be that? That will be this. And conversely, if you take an element here, you can prove that it is here also. That is, every element, every integer which can, every number which can be written as in the form 2n minus 1 can be written in the form 2n plus 1, and every integer which can be written as 2n plus 1 can be written as 2n minus 1. So that means these two sets are one and the same. But suppose I take A as the set of all 2n where n is an integer, and suppose I take B as the set of all 2n plus 1 where n is an integer. This will contain all even integers and this will contain all odd integers. These two sets will be, what will be the intersection of A and B? A intersection B will be equal to the empty set. And what will be A union B? Set of all integers. Now consider A union B. We always have that A is a subset of A union B. If X is an element of A, it is clearly an element of A union B, because every element of A is here, some other elements are also there. So A is always a subset of A union B. Similarly, B is also a subset of A union B. So A is a subset of A union B and B is a subset of A union B also. Moreover, we have another property. If A is a subset of a set D and B is also a subset of D, then A union B is also a subset of D. A is a subset of A union B and B is a subset of A union B. Moreover, if A and B are both contained in, if A is a subset of D and B is a subset of D, A is contained in D and B is contained in D. So if both A and B are contained in D, it follows that A union B is contained in D. How to prove this? We have to take an element of A union B. If you take an element of A union B, it is either element of, there are two cases. X is an element of A, X is element of B. If X is element of A, then X is element of D. Therefore, X is element of D. Now, the case 2, X is element of B. If X is element of B, B is contained in D, therefore X is element of D. In that case also we have that X is element of D. So in both the cases we have that X an element of A union B is in D. That is A union B is contained. Now what is the meaning of this? This means that A union B contains A and B, and that is also the smallest set containing both A and B. Because if D is any set containing both A and B, A union B is contained in D. That is, A union B is the smallest set containing both A and B. In a similar fashion, we can prove that A intersection B is contained in A intersection B is contained in B, and if a set D is contained in A and contained in B, then what happens? If a set is contained both A and B, then D is contained in A intersection B. Because if D is contained in both A and B, then we can see that D is contained in A intersection B, since if you take an element X of D, it is in A, it's in B, therefore it is in A intersection. So D is contained. This can be interpreted like this. A intersection B is the largest set which contains both A and B. If you take any set contained in both A and B, that set is contained in A intersection B, which means A intersection B is the largest set contained in both A and B. So these two results gives you, they are not very tough, but they gives you that there is a relation between the relations of set inclusion and the operations of union and intersection. We were discussing the commutativity and associativity of set operations like union, intersection and symmetry difference. There is another property called distributivity. What is distributivity? We say that multiplication is distributive over addition. For numbers, we say that multiplication is distributive over numbers. That is A dot B plus C is equal to A dot B plus A dot C. This is distributivity. Distributivity of multiplication or addition. In set theory, we have A intersection B union C is equal to A intersection B union A intersection C, and A union B intersection C is equal to A union B intersection A union C. That is, intersection is distributive over union and union is distributive over intersection. Both are there. But in numbers, we are only having that multiplication distributive over addition, but addition is not distributive over multiplication. This is not true. A plus B dot C may not be equal to A plus B dot A plus C. This result is not. That is, addition is not distributive over multiplication, but multiplication is distributive over addition for numbers. But in set theory, union is distributive over intersection and intersection is distributive over union. Both are there. Now, how to prove these results? Let me take one of them. Let me take the first one. In order to prove this, I want to prove that this is a subset of this and this is a subset of this. Now, let me take this part, that is A intersection B union A intersection C is a subset of A intersection B union C. First, let me prove this part. And then I will prove that this is contained in this also, and combining I will get the equation. That is the strategy. So, how to prove this? Usually, we take an element of the left hand side and prove that it is an element of the right hand side. That is the standard procedure. But here, let me try a different approach. Here, A intersection B is a subset of A. I mentioned that earlier. A intersection B is a subset of A. Because if an element is in A intersection B, that is in A and B, surely that is in A. So, A intersection B is a subset of A. And A intersection B is a subset of B. And B is a subset of B union C. And therefore, A intersection B is also a subset of B union C. Now, we have that A intersection B is contained in A and A intersection B is also contained in B union C. And what is this set A intersection B union C? That is the smallest set, that is the largest set contained in both A and B union C. So, what is the relation between this and A intersection B? So, what is the relation? So, we have that A intersection B. Sorry. What we have? We proved that this is contained in. So, combine we will get that A intersection B is. So, A intersection B is contained in what? A intersection B union C. Because A intersection B is contained in A intersection B is contained in B union C, and consequence of these two statements is that A intersection B is contained in their intersection. Now, similarly, we can prove that A intersection C is also contained in A intersection B union C. Similarly, by interchanging B and C. Now we have that A intersection B is contained in this and A intersection C is contained in this. If that is the case, then what happens? Then we have that A intersection B union A intersection C is also contained in A intersection B union C. Now we want to prove the other thing, that is, we want to prove that A intersection B union C is contained in A intersection B union A intersection C. For that you can use the usual method. You take an element here, it will be in A, it will be also in B union C. So there are two cases, it is in B and it is in C. If it is in B, then it is in A and B, therefore it is in A intersection B. If it is in C, it is in A and C, therefore it is in A intersection C. So in both the cases, it is in this union. And combining, you will get that these are equal. And a similar way, you can also try to prove the second result. The interesting thing is that even though for numbers, multiplication is distributive over addition, but addition is not distributive over multiplication. But in the case of set theory, intersection is distributive over union and union is distributive over intersection. Such a relation is there. When you look at the properties of this union, intersection, etc., you will note that a kind of duality is there. Because most of the results occur in pairs here. For example, these two. How will you obtain the second one from the first? By interchanging union and intersection. That is the case with most of the other results we put. For example, A intersection A is equal to A. Corresponding to that, there is a relation A union A is equal to. When you have A is a subset of A, sorry. But we have this A union empty set is equal to A. Corresponding to that, you will be having a relation A intersection the universal set U is equal to A. Here union is interchanged to intersection and empty set is changed to universal set. So in the set theory, once you have a relation involving the subsets of a particular set and the expression involving intersection, union, subset, superset, empty set, universal set, etc. If you have any such expression, and which is true for all such sets, and if you replace union by intersection, intersection by union, empty set by the universal set, universal set by the empty set, subset by the superset, etc., you will get another relation, and that relation will also be, that equation will also be true. And that is called the duality. Because of that, most of these set theoretical results occur in pairs. And actually, this is a consequence of a property of a structure called Boolean algebra. What is a Boolean algebra? Boolean algebra is one way of abstracting the set algebra. At the same time, it is also the abstraction of the algebra of logic. And at the same, there is also an abstraction of the switching circuits. Actually, this is started by George Boole. In 15 to 1864, a British mathematician. He had written a work in 1847, The Mathematical Analysis of Logic, being an essay towards a calculus of deductive reasoning. That was published by Boole in 1847. And in 1854, he published another book, an investigation into the laws of thought, mathematical theories on which are founded the mathematical theories of logic and probability. It was he who is responsible for this introduction of the subject Boolean algebra. His original aim was to study the algebra of the laws of thought. And interestingly, this algebra is slightly different from the ordinary algebra of numbers we are familiar with. Abstractly, a Boolean algebra is defined as a non-empty set X with two binary operations, addition and multiplication on it, and also a unary operation of taking complements, satisfying some axioms, namely both addition and multiplication are commutative, both addition and multiplication are distributive over each other, and both addition and multiplication is having identity element, namely 0 and 1. 0 is the identity element with respect to addition, and 1 is the identity element with respect to multiplication. And the other property is that x and its complement, the sum of x and x complement is equal to 1, and the product of x and x complement is equal to 0. So a system, a non-empty set with the two binary operations of addition and multiplication and a complementation, unary operation of complementation satisfying these four axioms is called a Boolean algebra. And one typical example is the power set of a set with instead of for addition you can take union, for multiplication you take an intersection, and you take for unary operation of complementation you can take the complementation with respect to A, and then all these axioms are satisfied. This is one typical example of a Boolean algebra. If you take the set of all propositions as a Boolean algebra with disjunction as the sum operation and conjunction as the product operation and negation as the complementation, there is also a Boolean algebra. Now, one interesting property of the Boolean algebra is that this is having a duality, because the addition and multiplication, both of them are treated in a similar fashion, unlike what we have in the ring of numbers. In the ring of numbers, multiplication is distributive over addition, but addition is not distributive over multiplication. But here, it's completely symmetric. All the properties of addition are also satisfied by the properties of multiplication. So you can even interchange multiplication and addition. So in the study of Boolean algebra, we have this duality. And as a special case, we have the duality in set theory and logic also. In logic also, the properties occur in pairs. So there is a very important aspect of set theory. Presently, we are not dealing with Boolean algebra. Another interesting relation is this. The complement of A union B is equal to A complement intersection B complement, and A intersection B complement is equal to A complement union B complement. That is, complement of a union is the intersection of the complements, and complement of an intersection is the union of the complements. These two are called De Morgan laws. Note that they also occur in pairs. Now, in fact, there is a De Morgan law in logic also. What is the De Morgan law in logic? That is negation of P and Q is logically equivalent to negation not of P or not of Q. This is one of the, and similarly there is another law, not of P or Q is logically equivalent to not of P and not of Q. Actually, these two results can be obtained as consequence of this. Once you have that. Because the complement of A union B is nothing but, what is it? X is an element of A union B complement means X is not in A union B. And X is not in A union B means X is not in A and X is not in B. That means X is in A complement and X is in B complement. That means X is in A complement intersection B complement. And then you can retrace here. So the proof is not difficult. Actually, these laws are named after De Morgan. The name is Augustus De Morgan. 1806 to 1871. But of course, I think the logical De Morgan law was known even to Aristotle, who started the logic as we know. So may not be an original contribution of De Morgan. But usually the theorems and properties etc. are named in mathematics for the convenience of that. So just because something is named as, say, Pythagoras theorem or Euler's theorem, that does not necessarily mean that that was the first invented by that particular person. You can just take it as a tag, a label assigned to a particular property. Because you need not read much into that, because many of the time the mathematician mentioned may not be the correct person. In fact, Pythagoras theorem was not invented by Pythagoras, and it was not even first proved by Pythagoras. and it was proved by many people from many civilizations earlier than that. So you can just treat them as labels. So De Morgan law, these are very important, and I think I suggested a proof for this, and similarly you can prove this also. What about this A intersection B, A union B intersection C, and A union B intersection C. Are they equal? No. They are not equal in general. You can get convinced of this by drawing just the Venn diagram of these two. They are not equal in general. But suppose A is a subset of C, then these two are equal. If A is a subset of C, then A union B intersection C is the same as A union B intersection C. Conversely, if this is true, then we can get that A is a subset of C. I am not proving this. I am suggesting this as an exercise for you. That is, A is a subset of C if and only if A union B intersection with C is the same as A union B intersection C. Once you have a relation like that, then immediately a dual. So what is the dual statement of this? C is a subset of A if and only if A intersection B union C is equal to A intersection this is also true. Both ways. That is, if C is a subset of A, this result is true, but if this result is true, then one interesting thing is that B is having no role. Whatever be your B, whatever be the set B, you are having this property. There is one interesting fact about it. Interestingly, the second relation can be proved from the first. How? You take the complement. Suppose this is true for every set. Suppose that the first result is true for every set. Then the second result is also true for every set. Why? If this is true for every set, this result is also true for A complement, B complement and C complement also. Then what will you get? You will get A complement contained in C complement if and only if A complement union B complement intersection C complement is equal to A complement intersection B complement intersection C complement. Am I right? Okay, sorry. is A union B complement intersection C union. The same thing. This rule with A, B and C replaced by their complements. So if this is true for every A and B, every A, B and C, this is also true since A complement, B complement and C complement are sets. Now when this happens, A complement is a subset of C complement. A complement is a subset of C complement if and only if C is a subset of A. And what about this equation? What about this equation? You can also rewrite that equation. This A complement union B complement intersection C complement can be written as, first here apply De Morgan law. What is A complement union B complement? That is A intersection B, the complement of that, intersected with C complement. And what is this? Intersection of the complements. Intersection of the complements is the complement of the union. What will get? What will get? You get A intersection B union C, the complement. Similar way you can also rewrite the other thing. That is, this part is written as a complement. This can also be written as a complement. So then you will get the two equation between two complements, and from that you can reduce this. So from first equation you can prove the second equation, and from the second equation you can prove the first equation. Oh, but that doesn't help us unless we prove one of them. So if you can prove one of them, the other follows by this process. So I am not giving detailed proof of these results. These are all given to you as exercises.